So here we're going to look at polar form of a complex number. Remember again, we're assuming here that as most of this material you'll find that z is x plus iy. Polar form of a complex number is well known. It's not just unique to complex numbers. Polar forms before. So these are polar coordinates. X is our cos theta and y is our sine theta. So the idea is to go from your xy variables to r theta. I don't want to say coordinates because these are variables right now. So anyway, if you substitute this in, this means that z now becomes r cosine theta plus I r sine theta. And then we can, of course, write that more like this. So let's look at a quick example of how we do this conversion. Let me do this one here for you. Minus 3 plus 4i. Minus 3 plus 4i. Of course, in order to do this, we need to find r and theta. Now, r would be the modulus. So r would simply be the size or the modulus of minus 3 plus 4i. So it is equal to the square root of 9 plus 16. Turns out to be 5. Now, on the other hand, the argument of minus 3 plus 4i is going to be equal to, remember for this, always it's a good idea to draw very quickly the Argand diagram. So you have minus 3 plus 4i, so minus 3 means, and here is 4. So this is our Argand diagram. So now we do know, now we know how to calculate the angle. In this case, it'll be pi minus, so it'll be pi minus tan inverse of 3 over 4, which turns out to be 2.214. Okay, so we have the argument. Now that we have the argument, we can write minus 3 plus 4i as 5 times cosine 2.214 plus I sine 2.214. Just to be sure here, just to remind you, this is your angle. This is the angle we're looking at, theta. So that's why it's pi minus, because it's going to give us something, this angle here. So anyway, okay. So some interesting results. If we have two complex numbers, z1 and z2, and their polar forms are r1 cosine theta 1 plus I sine theta 1, and similarly theta 2 and r2, then we end up with the following situation. r1, r2, take out the common, and you have cosine theta 1 plus I sine theta 1 into cosine theta 2 plus I sine theta 2. Now, if we open up all the brackets, we end up with this cos theta 1 cos theta 2 minus sine theta 1 sine theta 2. Okay, that'd be the real part. And then you'll have I times you'll have sine theta 1 cos theta 2 plus cos theta 1 sine theta 2, cos theta 1 sine theta 2. So now, if you look at this, we should notice here the identities. This becomes theta 1 plus theta 2, and the other one is I sine theta 1 plus theta 2. So that's a very interesting little result. Okay. And of course, from this, we can get further results. For instance, we know that the size of z1, z2 from this is r1, r2. Okay. which means that we have basically mod z1 into mod z2. And in a similar way, the argument of the product z1 z2 is theta 1 plus theta 2, which is arg z1 plus arg z2. Alrighty, let's move on. Here we'll mention an interesting result that occurs, and that is we note using this that if we were to multiply z, the complex number z, for instance, here where we're saying z would be just r cosine theta plus I sine theta. If we were to multiply z by I, let's write down I in complex, in polar form. So it's I's modulus is 1, and then we have cosine pi over 2 plus I sine pi over 2. We know that would produce, that's equal to I. So this would mean that according to the definitions above, that Iz can be written as follows. It's r, okay, cosine theta plus pi over 2 plus I sine theta plus pi over 2. So that tells us that the argument increases by pi over 2, but the modulus remains the same. So in a quickly diagrammatically, if this was z, for instance, okay, then with this angle being 90 degrees, this would be Iz. Okay, so that's a very useful and important result, and for the engineering students, especially electrical and electronic engineering students, this is quite important when you study the theory of alternating current. Alright. Now, in a similar way, we could do the same for division, and it turns out that we start with z1, z2 equals, for instance, r1 cos theta plus I sine theta divided by r2, sorry, let's call it theta 1 and theta 1, cos theta 2 plus I sine theta 2. Okay, we start with this, and with a little bit of we can multiply and divide by cosine theta 2, the conjugate of the denominator, remember? Okay. And that results in the following. It becomes r1 over r2, as it is, but here we end up with cosine theta 1 plus I sine theta 1 into cosine theta 2 minus I sine theta 2. And the reason for that is because the denominator becomes cos squared theta plus sine squared theta, which we know is equal to 1. So we end up with that, and of course that ends up giving us cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2. The same logic as before, multiplied through, collect the terms, and notice the trigonometric identity is useful here. Now this means that the modulus of z1 over z2 is r1 over r2, which is modulus z1 over modulus z2, number 1. That's what it helps with us understand. The other thing, it tells us that the argument of z1 over z2 is in fact the difference, theta 1 minus theta 2, so it's arg z1 minus arg z2. Okay, so that's another important result. I'm going to look at one example which combines all ideas, all these ideas now over z1, z2, and z1 over z2. So let's have a look at that example. So what we are asked to do is the following. You see this rather complicated fraction, a complex number, and we want to find the modulus and argument of this. In order to do that, rather than multiplying everything through, which will be quite cumbersome, we can exploit the ideas we've just looked at. So the modulus of this will become the following. Clearly, using the product and the rules that we have, this will become the modulus of 1 plus 2i squared. Okay, and this will become the modulus of 4 minus 3i squared. Okay, clearly, when you have z1, z2, modulus, that's modulus z1 into modulus z2, just to remind you. So clearly, if you have modulus of z squared, that's the modulus of z squared, right? So therefore, we end up with this, and of course, this is divided by not taking any division action yet. Okay, we don't need to, because once you have the modulus, then they'll just boil down to numbers, and they're easy to calculate then. Okay, so let's have a look now at this. So that's going to be 1 plus 4 square root squared into 16 plus 9. Okay, and no, this is cubed. This is cubed, so right. So put a square root on this. So this will become 3 over 2. Alrighty, and this one will be 9 plus 16 as well, and the power will be 4 over 2, and this one will be 4 plus 1, 3 over 2. So when we simplify, we're going to get here 5. 25 under the root is 5. 5 5 is 25, 25 5 is 125. All divided by... Okay, so that's going to be 625 multiplied by root 5 cubed. Some of this will cancel. I'll just leave you with a 25 here. No, sorry, with a 5. One sec. So that's going to be 5, and the result is it's going to turn out to be square root 5 over 25. Okay, right. And in the same way, so let's look at the argument, which looks like it might be very hard, but it's actually quite straightforward. Remember the rules state that z1, z2 argument of z1, z2 is argument of z1 plus z2. And so what you're going to have is the argument of z is equal to twice, of course, the argument of 1 plus 2i, all right, plus 3 times the argument of 4 minus 3i. Okay, and in the same way, then you're going to subtract, because we're dividing, so it's minus 4 argument of 3 plus 4i, and minus again because it's division and the power. So 2 minus I. So it's like if you brought up this, if you brought this up, it will be negative power here, and this, not this one, sorry, this original one. So bring it up, it'll be power minus 3, and this one comes up, becomes power minus 4. That's why you have a minus 4 multiplying it and a minus 3 multiplying it. And then you can just calculate the argument in the end. Okay, I'm going to move on.